Welcome to today's Explainer. If you're just starting out on your programming journey, you might feel like writing code is all about memorizing incredibly complex syntax, or, I don't know, typing as fast as a hacker in a movie. But the truth? The absolute best, most powerful code is actually just built on really clever, simple logic. So today we're going to demystify a frankly magical, time-saving programming trick. We're looking at a concept that will instantly upgrade the way you think about solving problems with a computer. It's called binary search. Basically, the hero's shortcut in code. So let's jump right in and learn how to actually think like a programmer. Okay, to really understand how computers search, I want you to picture a real physical scenario. Imagine you need to find one single word in a massive 1,000-page physical dictionary. Let's say you're looking for the word algorithm. Do you open the dictionary to page 1, read the first word, then the second word, and just keep flipping page by agonizing page until you finally hit the letter A, then L, then G? No way. That would take hours, maybe even days. What you naturally do is, well, you open the book somewhere near the middle, right? Say you land on the letter M. You already know A comes way before M, so you can completely ignore the entire second half of the book. You've just cut your problem in half. Then you flip to the middle of that remaining left half. Maybe you hit F. A is still before F, so you cut it in half again. Without even realizing it, you are intuitively using a highly advanced search strategy. And honestly, that is exactly what we are teaching the computer to do today. So let's look at the formal definition. Binary search is an efficient divide-and-conquer algorithm used to locate a specific item in a sorted collection. Now let's break those fancy terms down for a complete beginner. Algorithm? That is literally just a computer science word for a set of step-by-step instructions. Think of it like a recipe. Divide and conquer is exactly what you just did with that massive dictionary, taking a huge problem and dividing it into smaller, manageable pieces until you finally conquer it. And sorted collection? Well, a dictionary is sorted alphabetically. If those words were just thrown onto the pages completely at random, your halving trick wouldn't work at all. You'd be forced to read every single page. So binary search is really just the formal programming term for opening a sorted collection right to the middle and cutting the problem in half. This comparison brilliantly illustrates the sheer difference in strategy. On one hand, we've got the linear scan. Imagine this as a super tedious sequential line where you check item 1, then item 2, then item 3. It's painful, and if you have a massive data set, it is terribly, terribly slow. On the other hand, we have our divide and conquer approach. Instead of inching forward line by line, you take the entire massive block of data, chop it right down the middle, and completely discard the half you know you don't need. Boom, half your work is instantly gone. Then you just chop the remaining block in half again. The visual contrast here represents a massive, game-changing leap in efficiency. You aren't just working a little bit faster, you are fundamentally changing the geometry of how you search. The ultimate goal of binary search is to reduce search time from linear to logarithmic. Now, I know logarithmic sounds like some scary math jargon, but as a beginner programmer, you really just need to know it means incredibly fast because we keep having the problem. Let's put that into perspective. If you have 100 items, a linear search might take 100 steps. But if we have it, 100 becomes 50, 50 becomes 25, 25 to 12, then 6, 3, 1. It takes about 7 steps instead of 100. Let's scale it up. If you have 1,000,000 items, a linear search could take 1,000,000 steps. A logarithmic binary search? That takes about 20 steps. Yes, literally just 20 steps to search 1,000,000 items. We are transforming a frustratingly slow process into an incredibly elegant, lightning-fast solution. It's almost like magic. So how does this actually translate into code? Well, here are the 4 steps that make the magic happen. Think of this as a little narrative story we are telling the computer. Step 1, initialize boundaries. We tell the computer exactly where to start searching, let's call that low, and where to stop searching, which is high. Back to our dictionary, low is page 1, high is page 1000. Step 2, calculate the mid-index. We just tell the computer to find the exact middle point between our low and high boundaries. Step 3, evaluate. We look at that middle item and ask, hey, is this what we're looking for? And finally, step 4, repeat. Based on our evaluation, we adjust our boundaries and loop right back to step 2, repeating the whole process until we either find our target or our boundaries cross and we realize, oh, the target actually isn't there at all. Now, the absolutely crucial part is how that evaluate step actually works. Let's really deep dive into the brain of the algorithm. If the item at the middle, which we usually just call mid in code, is exactly equal to our target, boom, action, we return the index, we found it, job done. But what if mid is strictly less than our target? Well, since the whole list is sorted, Everything to the left of mid is obviously also too small, so our action is to discard that left side entirely and narrow our search strictly to the right half. Conversely, if mid is greater than our target, we know that entire right side is way too big, so our action is to toss out the right side and narrow our search to the left half. By writing code that follows this beautifully simple condition-to-action logic, you're telling the computer exactly how to throw away half the data every single time. Of course, every hero has rules they must follow, right? You can't just use this trick everywhere. First, and absolutely most importantly, sorted data sets. This is mandatory. If your data is just a disorganized random mess, discarding half of it is literally just throwing away random information. It will fail. Second, it's really best for static data, meaning data that doesn't change very often. Because sorting data takes time. If you're constantly adding new items and having to resort the whole thing every 5 seconds, you totally lose the speed advantage. Third, random access. This just means your data structure needs to let you jump immediately to any position, like a standard array. If you're using something called a linked list, where you actually have to walk through items one by one just to find the middle, well, the shortcut is ruined. And finally, use it for large inputs. For tiny little lists of, say, 5 items, linear search is perfectly fine. But when the data scales up, binary search becomes absolutely essential. Now, as a beginner, it's super easy to think of these algorithms as just, theoretical computer science exercises. But let me show you the real-world superpowers this trick provides. First up, database indexing. When you log into an app and it instantly retrieves your user profile out of hundreds of millions of users, that's largely because the database is using a form of binary search on sorted primary keys. Second, system libraries. Professional programming languages actually have this built right in. Java, for example, has a built-in tool literally called arrays.binary search. Pro developers use this stuff daily. And third, debugging. There is an incredibly famous tool called Git bisect. When a developer accidentally introduces a bug into the code, but they have no idea which update caused it, Git bisect uses binary search through the history of all the code changes to rapidly hunt down the exact moment the bug was born. This simple divide-and-conquer logic literally runs the digital world. Okay, but before you run off and start writing code, we do need to talk about the algorithm's kryptonite. Here are the common beginner traps you absolutely need to avoid. We already mentioned the first one, unsorted data. Using binary search on an unsorted array won't just be slow, it will yield completely incorrect results. Next up is boundary errors. This is the classic off-by-1 mistake. If your loop condition says keep searching while low is strictly less than high, instead of less than or equal to high, you might accidentally skip your target entirely if it happens to be the very last item you're checking. Finally, overflow. In some languages, if you calculate the middle by simply adding low and high together, and the dataset is astronomically massive, that combined number might actually be too big for the computer's memory to handle, causing a math error. The pro tip to avoid that? Just use a slightly different math formula. Calculate the gap between high and low, divide that by 2, and add it to the low. It's a tiny detail, but understanding these traps will save you hours of beginner frustration. So now that you know the shortcut, how will you apply this divide and conquer mindset to your very first coding project? You see, what we've unpacked in today's explainer isn't just a specific block of code for searching arrays. It is a fundamental philosophy of problem solving. Whether you're searching a massive database, hunting for a frustrating bug in your very first app, or honestly just trying to learn a massive new programming language, don't just scan linearly from start to finish. Look at the whole thing, find the middle, discard what you don't need, and conquer the problem. Take this logic, experiment with it, and really watch how it transforms your code. Thanks for learning with us today.